Welcome to the 8th lecture of Logic and Distributed Control System. So today we are going to discuss about the relation of digital gate logic to contact and coil or contact and coil logic. Last class we have discussed about the PLC programming languages, and we have understood in between all the languages the ladder logic is most popular, and also we have cited why the ladder logic to develop the PLC programming is popular. Now we are going to discuss today how the logic can be developed using only contacts and coil to build the PLC programming or ladder logic. And also we want to draw what are the relation with the contact and coil logic with the digital gate, that we are going to understand. So the objectives are, at the end of this chapter you will able to list the 7 basic digital gate types, draw their symbols and describe their function, show the relation of switch contact logic, that is relay or PLC ladder logic, to digital logic for each gate type, create digital systems and PLC relay logic diagram from process word description. So if a problem is described or a process is described by word, then how by reading that word we can create the digital systems as well as the PLC relay logic diagram or the ladder diagram. Convert from any one of the three programming system to any other for the process operation word description, relay logic diagram or PLC logic diagram, and the digital gate diagrams. It means that if the process operation word description is given, then we can develop the equivalent logic diagram or PLC ladder diagram or digital gate, or suppose digital gate diagram is given, we can find out the equivalent ladder diagram, or the ladder diagram is given, we can find out the equivalent gate diagram. So we want to see how these are related, because this will clear your concept to develop the logic for a complicated process. So now the 7 basic logic gates are listed here, that is AND gate, OR gate, NOT gate, exclusive OR gate, NAND gate, NOR gate, and exclusive NOR gate. So I am not going to discuss about the input output behavior of these 7 logic gates. It is expected that you are knowing the input output behavior, that is the truth table of all these logic gates. Now we want to understand, if we want to implement the ladder logic, or you want to develop the ladder logic using contacts and coils, then how for these 7 gates we are going to do that one. So this is the preliminary step. Already maybe some of you are knowing about this. So suppose there is a AND circuit, there is an AND circuit which having two inputs, IN1 and IN2. So you know that the logic for the AND gate is that the output is going to be high, or output is going to be on, or the output is going to be logic 1 only when the IN1 and IN2 are high logic, or IN1 and IN2 will be on. So that's why here you see these two inputs IN1 IN2 can be thought as two switches are connected in series, and with that a output relay is connected, and these two switches can be diagrammed as a IN1 and IN2, two normally open contacts in PLC ladder diagram. So what does it mean? Now whenever these two IN1 and IN2 are going to be on, then only the output 10 is going to be energized. So similarly, if you have multiple input AND gate where you can see that 4 inputs are there, then 4 switches will be in series, IN1, IN2, IN3 and IN4. The logic 12 or output relay is going to be energized only when these four switches are simultaneously on. Any of the switches are off, then the logic is, or the output 12 is going to be off. So this is the simple AND logic and its PLC equivalent. Now about the OR logic, so you can see that for the OR, three inputs are there: IN1, IN2, IN3, and from the OR logic we know that in between these three inputs any one is on, then output 17 is going to be on. So I can think in a relay logic, that is three switches are in parallel and any one of the switch is on, then the output 17 is going to be on. Then the PLC ladder diagram will be, we are using three normally open switches, IN1, IN2, IN3, and in between these three any one is on, then the 17 will be energized. Also the 17 will be energized that if three are on, three switches are on, or three contacts are on. So in this way we can see that the OR, how the OR logic is OR logic can be presented using the ladder diagram or the PLC logic. Then how we can represent the NOT logic? The NOT logic is interesting, that we have a switch IN22. If it is closed, then the LR logic will be high, and that LR is used as a normally closed contacts. If it is going to be high, then this LR is going to be open, and then the output 63 is going to be off. So this off, output relay 63 is going to be off with respect to the status switch, status of the switch SW22. Means if the SW22 is on, then at that time the output relay 63 is going to be off. So in this way the NOT logic is implemented, and equivalently the ladder diagram can be drawn as a IN22 is taken as a normally open switch, and 62 is taken another internal coil, and the same address has been used here as a normally closed switch or contact, that is CR62, and ultimately the output is 63. So when the IN22 is on, then the 62 is energized. If the 62 energized, then what will happen, that normally closed contact, that is 62, is going to be on. Then what will happen, the 63 is going to be off. So when the IN22 is on, then 63 is going to be off. And in normal cases you see that that it is normally closed. IN62 is normally closed, means the 63 will be on when IN22 is going to be off. So in this way the on logic, the NOT logic can be implemented using ladder diagram. And now we can have the NAND gate logic. So NAND gate, you can think that and NOT logic. So already we have implemented AND logic, and we have implemented the NOT logic, and which has to be ANDed. So what we can do now, we can first implement the AND logic by the first first line or first rung, and whenever the LR is going to be on, so the LR is going to be on, then output relay 27 must go off. So that's why what we will do, we will use a normally closed contact with the same address of LR. So what will happen, that whenever this IN1, IN2, IN3 and IN4 all are on, then 21 logic will be on, and whenever the 21 logic will be on, then 21 logic is used in the second rung as a normally closed contact. Then what will happen, this CR20 normally open contact is going to be off, and if it is off, then 27 is going to be off. So in this way the NAND gate logic can be implemented. And similarly we can implement the NOR logic also. So NOR logic, you can see that it is OR and NOT. So similarly we can have the IN1, IN2, IN3 are OR, and we have a logic 112, and the same address as a normally closed contact we have used in the second rung, and ultimately the output is indicated by 62. So if any of the switch is on, then the logic is going to be on, and when this logic is 112 logic is going to be on, then here 112 is going to be off, and if it is going to be off, then what will happen, the 62 is going to be off. So in this way we can explain, or we can find out the equivalent ladder logic of a NOR. So in this slide, the other two gates like XOR or XNOR is not shown, so I'm going to leave that for you. You will implement the both the things, that is switching logic as well as the ladder diagram. So for the XOR and XNOR, what will be the equivalent switching logic, and what will be the PLC ladder diagram that you are going to do. So now sometimes you may have to program a PLC in the Boolean algebra system, which is a shorthand method of writing gate diagrams. So here we are going to solve 4 examples of how to convert a word description into ladder and gate diagram, 3 examples of conversion from ladder diagram to a gate diagram, and 3 examples of conversion from gate diagram to a ladder diagram we are going to show, along with some additional word problem we are going to deal. So now first thing, 4 example of how to convert a word description into ladder and gate diagram. So first example, you see, this is the word description has been given. The output 22 is to be on only when either input 7 and 8 are on, or if input 17 and 18 are on, output 122 can be on when all the 4 inputs are on. So now to develop this logic, you can see that we have to, so how we will build the logic here. Now we have the power lines. Now we have to energize the output. The name has been given for the output is 122. Okay, so now what is the condition? The condition is saying that it is going to be on, okay, either input 7 and 8 are on. So definitely the 7 and 8 are ANDed, okay, and another set of inputs 17 and 18 are on. So now another set of inputs are there, that is 17 and 18 are on, and it has been said that that output 122 can be on when all the 4 inputs are on. So definitely this 4R will be in OR logic to energize the output 122. So in this way you can develop the logic for what the word description has been given, which is shown in here with the PLC ladder diagram, and you can write the Boolean expression also. You see 7 and it is 7 or with 8, okay, sorry, 7 and 8 basically they are ANDed, okay, and it is OR with 17 and 18. So this way you can write the Boolean expression also. So conveyor C, the next example has been given. Conveyor C is to run when any of the 4 inputs is on. It is to stop when any of the 4 other inputs is on. Hint, use push button. So here we are using push button switches. So for the push button switch, we can say that if it is normally on NO contact, so it will be like this, and if it is normally closed contact, it will be something like this. So now there are 4 switches to make the input on, and another 4 switches are make the input off. And what is the condition? The run when any of the 4 inputs are on, and stop any one of the 4 other inputs is on. So then what we can do, the things can be realized in 2 ways. If all the 8 switches you are using normally open, then this could be the possible representation that you see 4 1 2 1 2 3 4 4 normally open switches are odd as a start, and another 4 normally open switches are taken for the stop, but after ORing it, we are passing through a NOT logic because it is going to be used for the stop, and then the both the logics are ANDed to make the conveyor C on or off. Or you can do that for the stop switches. Normally we will take the normally closed switches. So then if you are going to push, then it is going to going to have no contact. Then what will happen? Then automatically it is going to be off. So that's why here you will find that we are using 4 normally close contacts, IN1, IN2, IN3, IN4. These are in series which are working as a stop switch, and IN1, IN11, IN12, IN13 and IN14 we are using in parallel as a on switch to either make conveyor belt on or off. So you see when they are normally closed, then the power can flow, and if any one 11 12 13 and 14 is on, then definitely the conveyor is going to be on. And if in between, if we withdraw any one of the stop switch, IN1, IN2, IN3, IN4, then what will happen? The conveyor is going to off. So that is the logic we wanted to develop with example 1.2. Now 1.3 is very interesting. When a start button is depressed, the motor runs. By sealing it, continues to run when the start button is released. Either stop buttons of the motor stops the motor when depressed. Okay, so here when a start button is depressed, the motor runs. By sealing it, continues to run, and when the start button is released, either stop buttons either stop button stops the motor when depressed. So here basically we are using two switches. Okay, two switches for the stop. So normally the stop switches we will take normally closed. So you can say that it is IN1 and IN2. Okay, and we have another two switches which is the start, which is for start operation. So here we can do in this way. Suppose this is IN1 and IN2. So another two switches we will take in parallel. Okay, so this is IN1 and this is 2. So this is closed, and this is 3 and 4, and here one motor is going to run. Now you see, whenever if any one of the three in between 3 and 4 is closed, the motor is going to run. But it has been told that seal operation means these 3 and 4 are the stop button switches. So what is the work of the stop button switches? So suppose this is the switch. So as long as you push it, it is going to be closed, and if you release it, then the motor is going to be off. So to avoid that one, what we will do along with this logic here, we will use a contact with the same address of the motor. Then what will happen once this motor is start? Okay, means suppose 1 and 2 is normally closed, in between 3 and 4 any one is on, then motor is going to be on. Once the motor is going to be on, then this switch with the same name or the contacts with the same name will be closed. Okay, and even if you release the 3 or 4, then the power is going to be flow in this direction. The power is going to flow in this direction because this is on, means this has to be closed. So now it will be remain on. Okay, to make it stop, these stop switches will be used. Means if you if you off any one of in between 1 and 2, then motor is going to be off. So in this way you can develop the gate logic and the relay logic and the ladder diagram for this problem. Okay, now the word problem example 4, the process fan is to run only when all of the following conditions are met. Input 1 is off, input 2 is on, or input 3 is on, or both 2 and 3 are on. Input 5 and 6 are both on. One or more input 7 and 8 or 9 is on. So you see this all condition has to be made to get the process fan run. So basically the process fan is to run only when all the following conditions are made. So it means that these conditions are actually ANDed. So individual condition we have to build, and ultimately all the logic has to be ANDed. So that's why input 1 is off, so that's why 1 we have taken with a negative logic. Then 2 or 3, 2 and 3 is odd. Input 5 and 6, then 5 and 6 is ANDed, and 7, 8, 9 is odd, and all the logics are now ANDed, such that if all the conditions are met, then only the process fan is going to be on. So this is the logic, and then easily we can convert it into the ladder diagram. So IN we have taken normally close. IN 7 IN 2 and 3 are odd, then 5 and 6 is ANDed, and 7, 8, 9 is odd, and altogether all logics are ANDed to get the output on. Okay, so this is the way you can write the or you can convert the word problem into the equivalent gate logic, and from there you can draw the ladder logic. Now we can do the other thing, that is, if a PLC ladder diagram is given, how to draw the equivalent gate diagram. Okay, draw the equivalent gate diagram and write the equivalent Boolean expression. So here it is very clear that 4 rungs are in parallel. So this is rung 1, 2, 3 and 4. It indicates that if the 4 rungs are in parallel, means they will be odd. Okay, so all this individual rung logic will be odd. So that's why you see OR logic has been taken, and its inputs are 4, 1, 2, 3, 4. Now you see individual rung. So first is 61 and 62 is ANDed. So 61 and 62 is ANDed. 63 is directly connected to the OR. 64 is also directly connected to the OR, and 65 and 66 is ANDed. 65 and 66 is ANDed, and then it is given to the OR logic. So in this way, and also you can write the equivalent Boolean expression also. And then we are going to understand the second example. Draw the equivalent gate diagram and write the equivalent Boolean expression. So here you see we have 3 rungs, 1, 2, 3. They are in parallel. It means that 3 rungs has to be odd. So to get the 15 logic 15, so these 3 rungs has to be odd. So here we are ultimately getting OR logic to get the 15. Now we have to implement each of the rung. Now 1 and 2 is ANDed, so 1 and 2 is ANDed and given as an input to the OR. 5 and 7 is ANDed, 5 and 7 is ANDed, given to the OR. And now to implement the third rung, you see 8 is ANDed, 8 is ANDed, you see 8 is ANDed, one AND, but 10 and 11 is odd, then it is ANDed with 8, and 10 is inverted. So 10 is inverted, here one bubble is there, and 11 is connected to build the OR logic, and ultimately it is ANDed with 8, and which is given as an input to the OR logic. So in this way you can convert a PLC ladder diagram to a equivalent gate diagram, and from there easily you can write what will be the equivalent Boolean expression. Now the example 3, draw the equivalent gate diagram and write the equivalent Boolean expression. So now you see here very interesting thing that how many branches are there? Here you can see that here basically two branches are there. This is 1 and this is 2. So this logic 1 and logic 2 has to be odd to get the Z. So Z we are ultimately getting a OR logic, that is F. Now we have to build individual logic 1 and logic 2. First you concentrate on the logic 1, how it is can be realized. So PQR are this PQR three switches or contacts are odd and Q is inverted. So you see PQR are odd and Q is inverted, and which is ultimately ended with UV logic and WX logic. So UV logic, how we will develop? Now UV is also ended. Sorry, UV is also odd. So UV is odd with the B logic. Fine. Then it is ended with W bar. So you see W bar and X. So all these four things are ended with the E gate, E AND gate. Then how you will get the logic 2? The S and T are odd, ANDed with Y. So S and T are odd with the C gate and Y is ANDed, and ultimately it is given to the F logic. So in this way you can build the logic developed here. And most interestingly, I think the next example we will do, where we can see that if a logic diagram is given, then how to build the ladder diagram, that is also is required, because these are the things will clear your concept, and later on when we will deal with the complex problem, this thinking methodology is going to help you. So now you see the AND 1 and 2, which is odd. So here, from here you can guess that obviously in the ladder diagram two branches will be there, okay, where this is logic 1 and this is logic 2, which has to be odd. So that's why two branches, you see two branches are there. First branch is logic 1 and second branch is logic 2, and the logic 1 is 101, 103, 105 are ANDed. So 101, 103, 105 are ANDed. 111, 113 are ANDed. 111, 113 are ANDed, and then both are odd. So both are odd here, and we are getting the final logic R. And also we can write the equivalent Boolean expression. We will move to the second one. Okay, so now here you see, now final, to get the final aim, we are using a AND logic. It means that there will be no branch or no rung to realize the aim, because all this logic has to be true simultaneously to get the aim logic high. So now that's why all these three logics has to be ANDed. So A, B, C are odd, which is ANDed with D, E, F. D, E, F are odd, and then it is ANDed with G, and that is H is inverted. So that's why normally close contact we have taken for the H, and we are realizing the logic M. Okay, so in this way we can convert a ladder diagram to a gate diagram to a ladder diagram. Now this example is again, it is very important. Okay, so now you see S logic we are realizing with ending logic 20. Okay, and most importantly, you can see that you can, if you see this part only, okay, this part only, so it is odd. 19 logic is odd, then it is inverted to get the 20 logic. Okay, so now first you concentrate, if we want to develop this 17, 18, 19 logic, how we will do. So L, M, N, okay, they are odd where M is inverted. So L, M, N we have taken odd, but M is inverted. Fine. Then Q and R is ANDed. So again parallel branch, because this logic and this logic, 17 and 18 logic are odd. So definitely to realize the 17 and 18 logic, two rounds will require and they will be odd. So that's why L, M, N we have taken, and Q and R are ANDed. Okay, and then finally here it is odd, but you see it is inverted logic is going to 20. So then what we will do, we will take this one as a logic 1, means up to 19 you can say we are taking as a logic 1, and now the inverted logic of 19 is ANDed. So what we will do, the logic 1, the same address we will use as a contacts in the next line, and we will take normally close contact, okay, which is ANDed with R. So the same address we will here use R, which is ANDed with logic inverted logic 1 to get the final expression S. So in this way we can convert a gate diagram to a PLC ladder diagram. Okay, so here some additional problem, what problem also we will do, we will deal, where we will see that only using contacts we are going to contacts and coils we are going to realize, and these are very important with respect to industrial problems. Okay, draw a ladder diagram of a simple circuit with one switch as a contact and one output as a coil. As the switch is open or closed, the output goes on or off. So here it is very simple. We have taken a switch IN001 and a output coil, that is CR17. So whenever the IN001 is on, CR17 is on. If it is off, then CR17 is off, and correspondingly how they are connected in the PLC, that has been shown, because IN001 is representing a physical switch. Basically it is connected with the input 1, okay, and and the CR17 is actually a physical output with the 17 number of pin of the output. It is connected, maybe it is a motor, or maybe it is a pilot lamp, or it is a solenoid valve. Okay, so this is the way we are going to develop the PLC logic. Okay, so now next problem, that is draw a ladder diagram of a simple circuit of start, stop, seal. So we have to do start, stop, as well as a sealing operation. Sealing operation means we are using the start and stop button are the push buttons. So if it is a start push button switch we are using, so as long as the push button is pressed, the motor will be on. If you release, then motor will be off. But we do not want to do that one. Even if the push button switch is released, the on switch is released, then also the motor must be on. That is called the sealing operation. When the start button is depressed, the coil energizes. When the button is released, the coil remains off. That is the sealing operation. If the stop button is depressed, the coil goes off and stays off. So now I will start with this simple problem. Then how we will start to write the ladder programming. That is very important, because it will help you to, if you go systematically, then you will find that it will be very easy for you to develop any complex programming also. So we will start with the output and we will see what are the conditions. So now suppose we have a motor which is CR17. Okay, so what we have to do with this output, now when a start button is depressed, the coil energizes, and the button is released, the coil remains off. If the stop button is depressed, the coil goes off and stays off. So we must have a stop button. So stop button must be taken as a normally close, and I'm giving the name, suppose IN002. Fine. So if suppose it is connected, okay, so now suppose it is connected. So if you off it, CR17 is going to be off, and if it is normally closed, then CR17 is on, there is no problem. But now we have to use a start button. So start button, it is normally open, okay, and if you connect it, and suppose the name I am giving IN001. Fine. So now if it is on, CR17 is on, but thing is that if it is released, when the button is released, coil remains on. So how you can do the sealing operation? Now we can use another contacts with the same name of CR17. Okay, so even if IN001, suppose IN001 is on, CR17 is on. Now if IN001 is released, CR17 is still will be energized, because by making the IN001 on, CR17 actually is going to be closed, and only way to stop it by releasing the IN002. If you release the IN002, then the current is not going to able to flow through the CR17. Okay, because here it is going to break. Here if you off it, here it is going to break, so no current is going to flow, so CR17 is going to off. So this operation is known as sealing operation. Okay, so using the same name of the coil as a contacts in the parallel of the on switch is known as sealing operation. Okay, so which is shown in the next diagram. Here you can see IN001 CR17. Okay, so if this is the condition, and the hardware diagram will be like this. Okay, so this operation is also known as the latching operation. Okay, so latching operation is also it is known that we are using the same contacts as a means same the name of the coils as a contacts. That is the sealing operation you can see here. Okay, now a little bit more complicated program, that is draw a ladder diagram of a standard forward reverse circuit. Means suppose there is a motor which can go forward direction and which can go reverse direction, but what we have to do, now each direction coil has its own start button. Okay, so each of the direction, for the reverse one start button, for the forward another start button. The single stop button stop either coils operation, but we have to use a single stop button. In the circuit you must push stop before changing direction. So here another thing you have to do, that if we want to go from the reverse to forward or forward to reverse, then one circuit must be off first, then we will go to the another one. Okay, interlocks are provided so that both outputs cannot be energized at the same time. So it cannot happen that both the circuit will be energized simultaneously, that is reverse and forward. You have to do an arrangement which is called interlocking. Okay, so at a time only the reverse or the forward circuit is going to be energized. So let us try the things. So now, as I said, that you always start with the outputs. Okay, so we know that the outputs is going to be the two outputs. Okay, one is forward circuit and another is for reverse circuit. Okay, so suppose this is CR17, control relay 17, and CR18. So these are the two outputs, and it said that it having single input stop button. So IN001 we are taking as a stop button that is normally closed. Okay, but it having different on switches. So then IN002 and IN003 we are taking as on switches, and we are using suppose push button. So for the sealing operation, what I will do here, I will use CR17, and here I will use CR18. Okay, now it is very simple. You see, when IN001 is on, then if you start IN002, then CR17 is going to be energized. Once it is energized, and then CR17 has to be energized, because even if IN002 is withdrawn, means it is a push button, so it is going to flow the current through the IN001 to this. And then if you want to stop, then with the IN001 you have to stop. Okay, and again if you on if you want to on the reverse circuit, then you can make the switch IN001 again close, then you have to push the IN003 on to make the reverse circuit on. But thing is that if anyone simultaneously closes the switch IN001 and IN003 simultaneously, then what will happen? Then the logic will be in a confusion that whether the motor, same motor, is going to be in forward direction or reverse direction. So for that, to meet that confusion, we need a interlocking. Okay, so suppose this is not there, we have to provide interlocking. It means that whenever the reverse circuit, forward circuit is operation, then reverse circuit, even if IN003 is on, reverse circuit is not going to be on. How we can do that one? Now we can use now another switch here or contacts here, okay, which is normally closed, and the address we will use CR18 here, and here we will use another normally closed contact, we will use CR17. Okay, this is called interlocking operation. It means that if the CR17 is on, then this will be off. It means that even if you press the IN003, the CR18 is not going to be energized. Okay, so this is the logic, and this other way you can verify that when you are making IN003 on, okay, and CR17 is de-energized, so it will be normally closed, and then reverse circuit is going to be on, and in that moment, if your IN002 is pressed, CR17 is not going to be energized, because CR18 at that time it is energized, which means that the CR18, which is a contact in the first rung, is going to be false. So in this way you can develop the interlocking technique. So here two things we have learned today, that is latching and as well as the interlocking. So these are very important concepts in the programming. So here the same thing has been shown. So now a little bit more complicated situation has been going to be dealt. What is that going to be dealt? That is, draw a ladder diagram of a forward reverse circuit. Each directions coil has its own start button and own stop button. Previously only single stop button we have used. Okay, here we have separate start button and separate stop button for the reverse circuit as well as the forward circuit. Direction can be changed without first depressing stop. So here in this logic, if you want to go for the reverse circuit, first you have to stop the reverse forward circuit, okay, and vice versa. But here now what we want, that direction we can change without first depressing the stop. Suppose if we want to go for the reverse, then it is not required to stop the forward first. Forward automatically will be stopped whenever we are going to start the reverse. Interlocks has to be provided that both outputs cannot be energized at the same time at directional pilot light indicators. Means whenever the reverse is going on, then one pilot light will glow. When reverse circuit is energized, then another pilot lamp is going to glow. So let us deal with that. How? As I told you that always you start with output. So we have two outputs here, so CR17 and CR18, okay, and it is suppose forward circuit and it is the reverse circuit. Okay, now now we have to use separate stop button. So suppose IN001 and separate start button, that is IN002, and as I told that there must be a ceiling circuit, so it is CR17. Okay, so like that it will be connected. It is the normal operation. Now we have to see what are the other conditions. So similarly it is going to start with IN003 and it is IN004, and here the CR18. Okay, so like that. and we have to do this, that is the interlocking. So interlocking just now I have discussed. So here you can use CR18 and here you can use CR7. Only logic you have to develop that we can change the direction without depressing the op switches. How we can do that one means, whenever the IN002 is pressed, CR17 will be energized. So at that time we have to ensure that CR17 has to be stopped. Okay, CR17 has to be stopped. So now how we can do that one? So now we can use another switch with a close contact, okay, normally close, and we can give uh, that is sorry that is IN004, and here we can use that normally close contact, that is IN002. So how it is going to facilitate us this logic? Now you see, whenever you are pressing the IN002, okay, then this is going to be false, okay, and the CR18 cannot be energized, fine. And now whenever the CR17 you want to go for the reverse circuit, then when you are making this IN004 on, automatically the IN004 in the forward logic is going to be false, means it is going to be stopped. So without stopping the IN001 on IN003, only using the start switches you can make the forward and reverse circuit off. So in this way you can solve this problem which is indicated here. Okay. And the last problem we are going to deal for today's, that is the example is an alarm system. There are 4 hazard inputs to the alarm system that go to on some operational malfunction occurs. The system operates as follows. How? If one input is on, nothing happens. If 2 inputs are on, a red pilot light goes on. If any 3 inputs are on, an alarm siren sounds. If all 4 are on, the fire department is notified. Means 4 hazard inputs are there. Okay. So if any one of the input is on, nothing is going to happen. In between these 4 hazard inputs, any 2 inputs are on, then pilot light goes on. If any 3 are on in between these 4 switches, the alarm siren should sound, and 4 are on simultaneously, then fire department is notified. So how we will do that one? So now here you have the 4 switches basically. Okay, so you can think that you have IN001, IN002, sorry, IN003 and IN004. Okay, so now if in between any of the two, this condition you just try to understand, if any of the 2 inputs are on, then the red light is going to on. Means we have to use the 2 combinations from this 4, and we have to make the OR circuit, then only we can implement this logic. And the same thing in between 3, in between 4, any 3, we have to see how many OR combination we can get, and then the siren sound. And the last one is easy. If the 4 are ended, then fire department is notified, and that has been realized in the next slide. That is, you see, the IN001, IN002, IN001. So these are the all possible combination, 1, 2, 3, 4, 5, 6, all possible combination amongst these 4 switches. Any 2 combinations are on, then CR17 means the red pilot light is going to on. And then taking 3 from the 4, then we have the 4 possible combination, and any 3 are on, then the siren is going to be on. Okay, and then if 4 switches are simultaneously on, then fire department is notified. So in this way, uh, we can develop the ladder logic for the problem 5. And today we have discussed what are the relation between the logic gates and the switch logic, as well as the relay logic, as well as the ladder diagram. And we have seen that if a word problem is given, then from there how we can develop the ladder logic, as well as the boolean expression, as well as the gate diagram. And if a gate diagram is given, then how we can find out the ladder diagram. If ladder diagram is given, how we can find out the gate diagram. So this, and here most important thing is that here all the logic we have developed using only contacts and coils. Okay, so in the next class we were going to start with other two very important elements, or the functions available in the PLC, that is the timer and the counter. But before that, we will discuss the registers available in the PLC, which will be helpful to understand the operation of the timer and counter. Also today we have discussed two important concepts, that is interlocking as well as the latching. Thank you.